Alright guys, let's take a look at an example here trying to find all zeros of a polynomial function. So it boils down to, again, just solving this equation, setting it equal to 0 and trying to solve for x. So one thing we can try is always factoring. You know, we kind of saw those in the first few sections where factoring would work. So just a quick try if we want to try grouping method maybe based on it having 4 terms. Let's see what happens. So with the first 2 terms, I see the only common factor is really going to be that x squared, and then we would be left with 2x plus 13. And then with the other terms, I don't know, anything goes into 34x and 15, so we could just bring a minus 1 out and have 34x plus 15. Oops, I mean minus 15. I forgot we took a minus 1 out. So it looks like, can I erase that? Oops, that's the highlighter. Anyways, let me just do this here. That's a minus sign, but either way, it's not going to work out with grouping because the shared, or the factor in the parentheses here doesn't match up, right? So we're not able to factor anything out front or whatever. So so this thing not really going to be factorable nicely, at least. So that's when we're going to have to resort to other options. And this is the step, like if you remember with quadratic equations, if they factored and then you could set them equal to 0, that was great. But if they didn't factor, which many of them don't, then we had to go to like a quadratic formula. Okay, so we're going to kind of go to plan B here now. We're at that point. So plan B, what you're going to want to do, you want to graph the function. Okay, so I want to graph it in decimals. Here's a little sketch of the graph, okay, with some of the key features labeled. We can see that it does have 3 real zeros. Okay, there's 1 there, and then 1 there. Okay, and the deal with this, sometimes people get confused. They just want to write, like, just graph it on a calculator and write those decimals and call it a day. But the issue with that is sometimes we need our answers to be exact. Okay, like that negative 8.583, that's probably an irrational number that has been rounded. Same thing with the 0.583. So what we need to get this going, you need to have at least one rational root. Okay, in this case, the 1.5 is rational because it does not go on forever. You know, that could be written as a fraction. 1.5 is really 3 over 2. So what we're going to do, we are going to say something like, to do our work, we're going to say from the graph, it's telling me that x equals 1.5 is a 0. Okay, so that's one of our answers right there. Okay, we also know the fundamental theorem of algebra will tell us that there's going to be 3 total zeros because this thing is a 3rd degree. Now this graph shows that all 3 of them are real. Okay, some problems you might only see 1 on the graph, which means that the other 2, or however many they are going to be imaginary. Okay, remember getting the square root under the negative. So here's what we're going to do though. We just need to get these other 2 values here and here as exact values. And here's how we're going to do it. We are going to say, since we know 1.5 is a 0, okay, that means that x minus 1.5 is one of the factors. Okay, remember factors get set equal to 0 to get the zeros. So we know, a little sloppy here, we know one of the factors is going to be x minus 1.5 because x equals 1.5 is a 0. So what that allows us to do is we are going to divide f of x, which was the original function, by x minus 1.5. And when we do that, when you divide something by one of its factors, you get the other factor. Okay, and then the other factor, in this case, since we started out with the 3rd degree, when we divide by a 1st degree function like we have here, we're going to end up with a quadratic, and then we have that magic formula, quadratic formula, right? So I'm going to assume we're going to be using synthetic division most of the time. Okay, it's a little bit quicker. So when you divide by x minus 1.5, you actually use 1.5 in the box. Okay, so just check we're actually using whatever the 0 actually was, okay, not the opposite of it. And then the coefficients of f of x up here were 2 for the x cubed, 13x squared, negative 34 for the x, and then positive 15. Okay, and let's run through our little synthetic process here and see what we get. Okay, so we always bring the first term down, bring the 2 down. 2 times 1.5 is 3. 13 and 3 is going to be 16. 16 times 1.5 should be 24. Okay, negative 34 plus the 24 will be a negative 10. And then negative 10 times 1.5 will be negative 15. And we're going to end up with this 0 remainder here. That's a must. If you don't get a 0 there, then something's wrong. Okay, because again, we knew x minus 1.5 was a factor. So when something is a factor, it should go into it with no remainder when you divide. Okay, so if you didn't get a 0 there, check your arithmetic or check that you used the correct number here. You didn't do the opposite or something by mistake. Okay, so here's what we have. So f of x, remember the big original polynomial, we knew x minus 1.5 was one of the factors. Now we just got the answer to our synthetic division problem is 2x squared plus 16x minus 10. Okay, that's just a quadratic. Okay, that is going to be solvable by the quadratic formula. Okay, we already solved x minus 1.5 equals 0. We knew that answer from the very beginning. Remember the graph showed 1.5. This is going to give us our other two answers, but we're going to be able to get them exact. Okay, so one option on this, if you recognize it, is that you can factor a 2 out of that and get yourself some smaller numbers to deal with if you want to. Then it will make your quadratic formula a little bit easier, because that's what we're going to have to use here is the quadratic formula. Okay, so if we do that, I'm just going to do the quadratic formula on this, because this 2, you could divide both sides by 2 basically, and that wouldn't impact anything. We would still have a 0 over here. So I'm just going to do quadratic formula to get my other two answers. So x equals the opposite of b, so negative 8 plus and minus the square root of b squared, so 8 squared, minus 4 times a times c, all over 2a. Okay, we just need to keep simplifying here. Negative 8 plus or minus the square root of 64 minus negative 20, so plus 20. So negative 8 plus and minus the square root of 84 all over 2. Okay, and we're just going to try to reduce that down a little bit farther and clean it up, combine any like terms, and, or I'm sorry, break down the square root, not really like terms either. Okay, so with the square root of 84, I know that 4 goes into that, and that's a perfect square. 4 times 21, right? So the square root of 4 is 2 root 21s, all over 2 still. And then the last thing you want to do, just to simplify, just take a peek, is this. All of these coefficients, are they all reducible by the same factor? And they are. In this case, we can divide each of them by 2. So I'll just get my other final answers. The negative 8 over 2 becomes negative 4. The 2 over 2 just becomes 1. And then we have the root 21. Okay, so those right here are the exact values of the decimals that we saw from the graph. Okay, if you do negative 4 plus the square root of 21, and you do negative 4 minus the square root of 21, you would get those decimals. But this is how we want to write the answer. Okay, we just like to be exact when we can. Okay, so that's kind of the process. If things are not factorable, you generally go to the graph, do a little synthetic division. Sometimes you have to do that more than once. Okay, if we would have started out with like a 4th degree function, we would have to have 2 rational zeros to do synthetic division twice in order to making it down into a quadratic. Okay, so this one though, it only had to happen once, but that's kind of the thought on that, and that is an example of how to find zeros exactly for polynomials.